Okay, students, welcome back. We're going to cover 6.3. Okay, 6.3 is on the kernel and a range of a linear transform. Okay. 6.3, okay, the kernel and range of a linear transformation. Okay. So let's start off with a definition. What is the kernel? Okay, and what's the range? Okay, let T go from V to W be a linear transformation period. The set of all vectors V such that they are an element of V such that T of V is equal to 0. Okay. So anything that transforms a vector into the 0 vector, that's part of the kernel. Okay, is called the kernel of T and is denoted the kernel of T, thus the kernel of T equals all vectors V in V such that the transformation of V goes to 0. Okay, that's the first definition. The second definition, so this is, what's going to transform and go to 0. The second definition is the range, which kind of think of as the output. Okay, so the range is just everything that I could get transformed as an output, including 0. Okay, so the kernel is a part of the range. It's just a very specific part of the range. Okay, but the range of the linear transformation okay, T as V goes to W is the subset of W consisting of all transformed vectors from V. We denote the range of T by Rng of t. Thus, the range of t is equal to all the transformations of t of v, okay, such that, okay, v is an element of v, okay, and t of v is a subset of w, but they don't state it here, okay, it's just like all the output values that I could possibly have is the range. Which kind of makes sense. Domain, you think maybe of a domain as the vectors v and the range as the outputs after they're transformed. Okay, for a matrix transformation, okay, for a linear transformation, such that t goes from R of n to R of m with m by n matrix A, the matrix of the transformation, or the matrix of T, matrix A, okay, then we can say that one, the kernel of T is equal to the null space of A, okay, so the kernel of T is equal to the null space of A, all the values that make everything 0. Okay, make the system 0. Okay, is the null space of A, and then 2. Okay. Okay, the range of T is equal to the column space of A. Okay, the null space of A is a subspace of Rn. Okay, where we're going from. And the column space is a subspace of Rm. Okay, where we're going to. Okay, which kind of makes sense. The output would be a subspace of have the output dimensions. The null space, okay, has is R sub n, which is the dimensions of my inputting vectors, my input vectors, okay, has the same dimension as the dimensions of the vectors that go into the transformation. Okay, number 1. Let T go from R3 to R2, be a linear transformation okay, with matrix A equaling negative, oh, sorry, it's 1, 1, negative 2, okay, 5, and then negative 2, 4, and negative 10. Okay, find the kernel and range of T. And the kernel and range of T. Okay. So the kernel of T is going to equal the null space of A. Okay, and the null space is going to be where this thing is equal to 0. Okay, it's AX equals 0. Where what values of X is this system of equations going to be equal to 0. It's homogeneous, my homogeneous solutions. Okay, so I'm going to get this guy to be 1, -2, 5, -2, 4, -10 times x1, x2, x3 is equal to 0, 0, 0. Sorry, just 2 zeros. 0, 0. Okay. Okay, so how can I solve this? So I can put this into an augmented matrix. 1, -2, 5, -2, 4, -10. Okay, and then 0, 0. And then I can REF that. And I just end up with, if I multiply the top equation by 2 and add it to the bottom one, then everything cancels out. And so I get 1, -2, 5, 0, 0, 0, 0, 0. Okay, basically I can REF it in one step. And so now I have this equation, x1 minus 2x2 plus 5x3 is equal to 0. Okay, and so I'm going to solve for x1. x1 is equal to -2x or positive 2x2 minus 5x3. Just like we did before, we're going to put in some variables so I can equate x1, x2, and x3. Okay, so let x2 equal s. Okay, let x3 equal t. Okay, and I can say that x1 is equal to 2s minus 5t, and so I can write the solution as in two variables as 2s minus 5t, comma, that's x1. x2 is s, okay, and then t. Okay. So I can say that this is x. This is my x. Okay, and so I got an extra parenthesis there. Sorry about that. Okay, and so yeah, I could rewrite this if I wanted to as I could pull out the s and t. So I just have some values. Okay, so I have some vectors that don't involve s and t. Okay, so this is, if I choose s, that's s times 2, 1, and then 0, plus t times -5, 0, and 1. Okay. Okay, and so that's about as far as I can go. So I can write the kernel of t is equal to, okay, all values of x in R3, okay, each of these have 3 components. Okay, all values of x in R3 such that, okay, in 3 space, such that x is equal to s times 2, 1, 0 plus t times -5, 0, 1. Okay, and I'm not looking for a basis. I'm just looking for what these values could be. And so I can stop at this point here. Okay. Okay, I might want to put in a little caveat that says S and T are elements of the real number system. So maybe put that in as well. Okay, but it doesn't necessarily need to be there. And we've assumed. Oh, were we gonna find the range as well? Yeah. Oh, yeah, yeah. So, let's look at, what this kernel is before we talk about the range. So the kernel is, is the two, is it a two-dimensional or three-dimensional? No, it's two-dimensional. Okay, the kernel is the two-dimensional. You're like, how is it two-dimensional? We'll talk about that in a second. Two-dimensional. Okay, I'm like I thought there was three dimensions. It is in three dimensions, although it's two dimensions because it satisfies a certain property. Okay, a two-dimensional subspace of R3. It's a two-dimensional subspace of R3. This isn't always the case. It just happens to be the case in this case. Okay, spanned by the linearly independent vectors two, 1, 0 and -5, 0, 1. Okay, geometrically, okay, it consists of all points lying, okay, in a plane. Since I only have 2 points and I didn't end up with 3 points, okay, since I only end up with 2 points, right, I can draw a plane through any 2 points, okay, in three-dimensional space. So that's why it ends up being two-dimensional, because I can fit all of the solutions in a two-dimensional plane. Okay. And all the points lying in the plane, in a plane, x1 minus 2x2 plus 5x3 is equal to 0. So within that plane, all of my solutions will fall. Okay. Does the plane exist in 3 dimensions? Yes, but the solutions are 2-dimensional. Okay. Okay, so what about the range? Okay, well, the range of T is just the column space of A. Okay, so what's the column space of A here? Well, okay, let's go through that. Okay, so if we look at A, okay, 1, -2, 5, -2, 4, -10. Okay, 1, -2, 5, -2, 4, and 10, right? Okay, let's look at the column space here real quick. Okay, so the column space is when I REF this thing, I end up with 1, -2, 5, 0, 0, 0. Okay, right? And so I have to go back to I only include the ones that have leading ones. only include the columns that have leading ones. Well, this only has a leading one for the first column. So my column space goes back here. Okay. So this is equal to the span. The column space of A is equal to the span of 1, -2. It's all the points that I can span with the vector 1, 2, 1, -2. Well, what are all the values that can span with -1, 2, and those are all the multiples of -1, 2. Think of it like a slope, and you have a specific line now because you have 1 point in 2 dimensions. And what are all the what can I span with this 1 point in 2 dimensions? Well, it would be a line along a certain slope. Okay, because I can only have multiples of that point, and that's going to span, okay, a certain line. So the range, okay, the range, if you kind of plug this in, and you got, say, say that we said that this was y1, okay, minus 2y2 is equal to 0, right? Well, then how could we relate those two? This would be y1 equals 2y2, right? Right? And so what's that in the equation of? It's an equation of a line with slope 2. Okay, so okay, so we have the range of t, the outcome of t can be -1, 2, and all the multiples of, sorry, 1, -2, and all the multiples of 1, -2. Okay, so the range of t is equal to all the elements of y, okay, such that, maybe I'll do y as a vector, okay, in R2, okay, R2, this is getting transformed to R2, okay, such that, okay, y is equal to R times the vector 1, -2, so all the multiples of 1, -2, such that R is an element of R. Okay, so that constant is an element of R. Okay. Okay, so the range, okay, the range is all points lying on the line okay, y1 equals 2y2, okay, period. So T maps all points in R3, okay, to this line. But those in the kernel get mapped where? To the origin. Okay. Well, that's kind of interesting. Okay, a picture might help here. Okay, let's look at a picture real quick. So if I have x1, x2, and x3, okay, then the kernel of T is a plane through which 2, 1, 0 and negative 5, 0, 1 go through. Okay, so maybe that's a point on my plane, and then 2, 1, 0, right? 2, 1, 0. Yeah, 2, 1, 0. Okay, so 2, 1, 0. Maybe that's a point, and my plane goes through, and it also goes through 0, 0, 0. Okay, because if I plug in zeros, I should get out 0, right? So if I plug in 0, 0, 0 to x1, x2, x3, okay, right here, I should get out 0, right? 0 minus 0 plus 0 is 0. So that does go through that plane. The origin is part of that plane. So if I draw a plane, I'll draw it like this. Okay, it is gonna go through the origin, and it's going to go through these other 2 points. Okay, so let's draw that plane. Okay, and this plane, okay, that plane is going to be called the kernel of T. Okay, so this plane, I'm going to do it in a different color. Okay, this plane, which is I'm going to put in red. Okay, this is going to get mapped now to my range of T, and the range ended up being a line, right? Okay, so if I have, okay, say y1, y2, y3. Okay, y1, y2, y3. Okay, y1, right? And so this is going to be a line in 2 space. There is no y3 in my line. Y3 is 0. Okay, and so this is a line in 2 space where the slope is 2. Okay, it's really slope of 1/2 if I were to solve for y2. But we're all good. We can just draw like that. That's going to be my range of T. Okay, my range of T is that guy there. But, and that's all the points, all the vectors in V. Say that this is V, right? So we've got V here. and we've got W here. Okay, vector space V to vector space W, but the kernel of T is going to get mapped where? Every single one of these from the kernel that's in the kernel in this plane is going to get mapped directly to the origin. No matter where it is on the kernel, it's going to get mapped directly to the origin. Okay, so it could be here, and it gets mapped to the origin. Okay, it could be anywhere on there, it's going to get mapped to the origin. Okay. Okay, but any value that is in V, okay, any value that could be in V, maybe I use green for this. Okay, if that is in V, then where is that going to get mapped to? It's going to get mapped to some place on this line. Okay. Every other point that's not in the kernel is going to get mapped to the line. Okay. That certain line. Okay, number 2. Let's go back to red. Okay, let T of P1 of R go to P2 of R. So the transformation that takes linears to quadratics. Okay, B, the linear transformation okay, defined by T of A plus BX equals 2A minus 3B plus B minus 5A X plus A plus B X squared. Okay, so all I have to know is A and B, and then, you know, in my linear, and then I can get my quadratic from this. Okay, find the kernel of T and the range of T. Okay. Okay, so the kernel of T is going to be equal to all the values of A plus BX such that, okay, when I plug it in to my transformation, okay, I get this equal to 0. I get 2A minus 3B plus B minus 5A X plus A plus B X squared is equal to 0. Okay, for all X. For all X. There we go. Okay, so what does this mean? Well, it means that 2A minus 3B must be equal to 0. B minus 5A must equal 0. And A plus B must equal 0, right? Because the only way to get a quadratic to be 0 is have all my coefficients be zeros. Otherwise, I don't have a quadratic. I mean, I don't have a 0. I have a quadratic. Okay. So okay, so I know that 2A minus 3B is equal to 0. don't know why I put parentheses there. And b minus 5a is equal to 0. Okay, so let's solve this. And we also know that a plus b must be 0. So what are the only solutions here? Well, if I multiply the bottom through by -2, 10, oops, not -2. I want, let's swap these around. Okay, this is b minus 5a equals 0. So this is going to be 2a minus 3b minus 5a plus b is equal to 0, equal to 0. Okay, and so if I multiply through by 3 on the bottom, -15, right, plus 3 is equal to 0. Okay, and so yeah, the only thing that a can be is 0. So a had to be 0. But if a is 0, and the only thing that b can be, okay, based on this guy here, is 0 as well. Okay, so b had to be 0. Okay, that's the only way for me to get all zeros there is for a to be 0 and b to be 0. Okay, and so what's the kernel of t? Well, the kernel of t are all transformations, all values of okay, the kernel of t, they are all the linear expressions that produce 0. Okay, all values of a and b that produce 0. So the kernel of t is really just a plus bx, but a and b are 0. So this is just going to be 0 plus 0x. Okay, and 0 plus 0x is just 0. Okay, so yeah, it's 0 in P1, okay, which is an element of P1R. Okay, so we could have 0 plus 0x if we really wanted to get it, say, oh, this is an element of P1R, but basically it's 0. The only thing that's going to get me 0 is 0 here. The kernel of T is 0. Okay, what's the range of T? Okay, what's the output going to be? The range of T is equal to, okay, all the outputs of T, the transformation of A plus BX, okay, such that A and B are real numbers. Okay, well, this just tells me, okay, that, well, the output is going to be the way that the transformation is defined is going to be 2a minus 3b, 2a minus 3b, okay, plus b minus 5ax plus a plus b x squared, such that a and b are elements of R. Okay. Okay, so let's distribute and collect on a and b. So this is 2a minus 3b plus bx minus 5ax plus ax squared plus bx squared where A, B are elements of R. Okay. Okay, and then this is going to be, okay, 2A minus 5AX plus AX squared. Okay, and then this is minus 3B plus BX squared, such that A and B are elements of R. Okay, so now I want to factor out my A. My A is going to be A times 2 minus 5x plus x squared. Factor out my B plus B times negative 3 plus x squared. And so my range is the span of 2 minus 5x plus x squared and negative 3 plus x squared. Okay. Okay, good. That's the range of t. Okay, let's look at what's called the general rank nullity theorem. Rank nullity theorem. Okay, the general rank nullity theorem. If T is a transformation that takes V to W, is a linear transformation, and V is finite dimensional, right? Then we can say that the kernel, which is the null space, okay, the dimensions of the kernel of T, okay, plus the dimensions of the range of T, which is my, if it was a matrix, it'd be my column space of A. Okay, that would be my null space of A, column space of A, okay, is equal to my dimensions of V, which if this was a matrix, it would be my rank. Okay, but where you have generalized it to now say any linear transformation, the dimensions of the kernel of T plus the dimensions of the range of T equals the dimensions of V. Okay. Okay. So let's check this for my examples that I did. Okay, so let's check this for example 1. Okay, for example 1, we had a matrix A. Okay, we had a transformation that went from R3 to R2. Okay, and okay. Okay, and if we look at the kernel of this, okay, the kernel, okay, of T. Okay, we could have written it as the span of 2, 1, 0 and -5, 0, 1. Okay, we could have written it like that. That's the kernel of T. Okay. It's all the values of all the x values that are in this span. Okay. Now that was our plane. Remember, we said that was a plane. Okay, and so how many elements are there in this span? Well, this has a dimension of 2. So the dimension of the kernel of T is 2. Okay. What about the range of T? What did we say what the range of T was? The range of T was our column space, which was the span of 1, -2. Okay, it was the span of 1, -2, which is just, okay, one vector. Okay, so the dimensions of the range of T, okay, is just 1. And the dimensions of V, well, that was in R3, right? So the dimension of V was R3, and R3 has a dimension of 3. And so it does check. That was for example 1. Okay, let's look at example 2. Okay. For example 2, the kernel of T, okay, was equal to 0. That 0 value that we got, that kind of a null value. Okay, and so what's the dimensions of the 0 vector? It's just 0. There's nothing there. Okay, so the dimension of the kernel of T is 0. And what about the range of T? Okay, what about the range of T? Well, the range of T, okay, we go back up here, the span of these two vectors. Okay, so 2 minus 5x plus x squared and -3 plus x squared. So I have two values there, two vectors. Okay. Okay, and so the range was 2. Oops, the range of, sorry, this was 2 vectors. Okay, which was the span. Gosh, this thing's kind of slow. Span of 2 minus 5x plus x squared and -3 plus x squared. Okay. So that's the range of T. Okay, and so what's the dimension of the range of T? It's 2. And so the dimensions of V, okay, is what? Well, it's P1R, right? And what did we say the dimensions of P1R? It was n plus 1, where P sub n, right? N plus 1. It was always one more, because we always have that constant term, is one more than the subscript. And so this is 2. Okay, P sub n plus 1 is 2. And so the dimension of V is 2. I should write it like this, I guess. Come on, erase. Dimension of P1R is equal to 2. Okay. And so that does check as well. Okay, so that's 6.3. And I'll see you in the next section.